projects. In this video, we are going to explain about the project title, an interpretable skin cancer classification using optimized convolutional neural network for a smart healthcare system. Introduction. Skin cancer originates from the epidermis, where abnormal cell growth occurs uncontrollably, forming malignant tumors that can potentially spread if not treated. The reduction of the ozone layer has increased exposure to harmful UV radiation. This radiation damages skin cells, heightening the risk of developing skin cancer due to accumulated cellular damage. Several factors, including lifestyle choices like smoking and alcohol intake, pre existing health conditions, infections, and environmental exposures, contribute to the formation and progression of malignant cells in the skin, amplifying the risk of skin cancer development. Clinical assessment of skin lesions is hindered by long waiting times for appointments and subjective interpretations by healthcare providers. These challenges have prompted the development of computer assisted diagnostic approaches aiming to enhance accuracy, efficiency, and impartiality in skin cancer diagnosis. The project aims to develop dependable deep learning models specifically designed for skin cancer classification. It seeks to address class imbalance issues in datasets, interpret the output of these models to enhance understanding, and propose a comprehensive smart healthcare system that leverages these technological advancements. The project utilizes the HAM 10,000 dataset, a comprehensive collection of dermatoscopic images representing various skin lesions. An optimized convolutional neural network CNN is employed to accurately identify and classify the 7 different forms of skin cancer depicted in the dataset. Objective. The project's core objective is to develop an advanced system utilizing convolutional neural network CNN that not only accurately classifies skin cancer but also offers interpretability. This aims to provide insights into the model's decision making process, enhancing trust and understanding. By leveraging CNNs, the project targets the creation of a method that improves accuracy and efficiency in diagnosing various forms of skin cancer. Transparency is crucial, ensuring that the system's decisions are understandable and trustworthy. The project employs CNNs, optimizing the performance with techniques like ADAM and RMS prompt, along with activation functions such as ReLU, Swish, and TAN. These approaches aim to enhance the precision of the model in accurately classifying skin lesions. The project relies on the HAND 10,000 dataset, a diverse collection of dermatoscopic images, to train, validate, and test the CNN model. This dataset's comprehensive nature enables robust training to classify various types of skin cancer. By leveraging CNNs and image pattern recognition, the project surpasses conventional methods in skin cancer identification. It emphasizes interpretability, providing understandable reasons behind the model's decision. This approach aims to enhance trust among healthcare professionals regarding the AI model's decision making process. Software and hardware requirements. Software requirements of the project are: application is Anaconda, primary language is Python, front end framework is Flask, back end framework is Jupyter Notebook, database is SQLite 3. Front end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements of the project are operating system of Windows, processor of 5.5 and above, RAM of 8 GB and above, hard disk of 25 GB and above. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This step involves importing necessary libraries and packages like TensorFlow, Keras, Pandas, and more, required for data handling, image processing, and model building. It sets up the environment for the project. Exploring the dataset. Skin cancer HAM 10,000. This section involves exploring the dataset, specifically the HAM 10,000 dataset, which contains a vast collection of dermatoscopic images representing different types of skin lesions. Exploratory data analysis EDA include understanding the dataset structure, distribution of classes, and initial visualization to gain insights into the data. Image processing using image data generator. Employing the image data generator from Keras for on-the-fly image augmentation during model training. Rescaling the image. Adjusting the image's pixel values to a specific range, usually between 0 and 1, for better convergence during model training. Shear transformation. Applying shear transformation to the images, altering their shapes by shifting parts of the image in a fixed direction. Zooming the image. Changing the image's zoom level, magnifying or reducing certain portions of the image. Horizontal flip. Flipping images horizontally, which help augment the dataset and enhance model robustness. Reshaping the image, ensuring that all images have the same dimensions or reshaping them to a standard size suitable for model input. Building the model, creating the architecture of the convolutional neural network CNN model. This involves defining layers, convolutional, pooling, dense, specifying activation functions, selecting optimizer, setting up loss functions, etc. The model architecture designates how the network learns from the input images and makes prediction. Training the model. Training the CNN model using the prepared dataset. This step involves feeding batches of augmented images through the model, adjusting the model's weight to minimize the defined loss function like categorical cross entropy, and validating the model's performance on separate validation data. The training phase aims to improve the model's ability to accurately classify skin lesions. Flash framework with SQLite for sign up and sign in. Integrating the Flash framework, a Python based web framework with SQLite, a lightweight database to create a user authentication system. Users can sign up for accounts and sign in securely to access the system's functionality. User upload an image for analysis. Allowing users to upload an image of a skin lesion for analysis through the developed system. This user interface provides a means for individuals to submit their skin images for classification. The given input is pre-processed. Before feeding the uploaded image into the trained model, pre-processing steps are applied. This involves resizing the image to match the model's input size, normalizing pixel values, and preparing the image to fit the model's input requirements. The trained model is used for prediction, the result. Employing the previously trained convolutional neural network CNN model to predict the type of skin cancer based on the pre-processed image uploaded by the user. The model leverages its learned patterns and features to make a classification prediction. Final outcome is displayed, presenting the final result or outcome of the prediction to the user. This involves displaying the predicted class of skin cancer, such as melanoma, basal cell carcinoma, and more. The outcome is communicated back to the user through the interface, providing the predicted diagnosis based on the uploaded image. Algorithms used. To implement this project, we have utilized the following algorithms. The first algorithm is CNN, Convolutional Neural Network. CNNs are a class of deep neural networks specifically designed for processing structured, grid-like data such as images. In this project, CNNs are utilized for their ability to automatically learn and extract intricate features from dermatoscopic images of skin lesions. They are pivotal in accurately classifying different types of skin cancer based on these learned features. Optimization algorithms, ADAM and RMS prompt. These are optimization algorithms used to update the model's weights during training to minimize the defined loss function. ADAM and RMS prompt are popular optimization techniques that adjust the learning rates for each parameter in the model, aiming to converge faster and more efficiently towards the optimal set of weights. Activation functions, ReLU, Swish, and TAN. Activation functions introduce non-linearity into neural networks, enabling them to learn complex patterns in data. ReLU. rectified linear unit. It's a widely used activation function that introduces nonlinearity by allowing only positive values to pass through the network. Swish. This activation function was proposed as an alternative to ReLU, aiming to enhance learning capabilities by smoothly integrating nonlinearity into the network. Tan. Hyperbolic tangent. Similar to the logistic sigmoid function, tan squashes the output to the range -1, 1, providing stronger gradients during training. Exception and DenseNet. These are advanced CNN architectures that offer improvements over traditional architectures like VGG or ResNet. Exception. It's an architecture known for its depth-wise separable convolutions, which aim to capture fine-grained features more efficiently, resulting in a more compact and accurate model. DenseNet. This architecture emphasizes dense connectivity between layers, allowing features to be reused more effectively and enabling better gradient flow, which can lead to improved accuracy with fewer parameters. These algorithms and architectures, including CNN, optimization methods, ADAM, RMS prompt, activation functions, ReLU, Swish, TAN, exception, and DenseNet, are critical components of the project. They are chosen and fine tuned to enhance the accuracy, efficiency, and interpretability of the convolutional neural network for precise skin cancer classification within the smart healthcare system. Comparison graph offer a visual breakdown of how a model performs across essential evaluation metrics. Models are compared with the parameters accuracy, precision, recall, and FN score. This is the accuracy comparison graph. On the x-axis we have accuracy score, and on the y-axis we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positive and true negative, to the total number of instances. This is the precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have FN score, and on the y-axis, we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. The algorithm, which is performing best in all the performance metric, will be used for prediction. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is model file which contains algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. So here I'm copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I am typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered. So click on sign in link here. So here we need to enter the username and the password and then click on login. We have logged in successfully. So here we need to upload the image to predict the type of skin cancer. Now click on choose file to upload the image. Select the image, click on open. Now click on upload button. So here we can see we got the result. This is the uploaded image and it is predicted as melanoctic nevus, non-cancerous disorder of pigment producing skin cells commonly called birthmarks or moles. Now we will upload one more image and check the type of skin cancer. Click on choose file. Select the image, click on open. Now click on upload button. This is the uploaded image and it is predicted as basal cell carcinoma, that is BCC, is a type of skin cancer that forms in the basal cells of your skin. Now click on try again and let us upload some more images. Click on choose file. Select the image, click on open. Now click on upload button. This is the uploaded image and it is predicted as benign keratosis like lesions, solar lentigens or seborrheic keratosis, and lichen planus like keratosis, BKL. Now click on try again. Click on choose file. Select the image, click on open. Now click on upload button. This is the uploaded image and it is predicted as actinic keratosis, solar keratosis, and intraepithelial carcinoma, Bowen's disease, which are referred to in this paper as AKIEC. Now let us upload some more images. Click on try again. Click on choose file. Select the image, click on open. Now click on upload button. This is the uploaded image and it is predicted as vascular lesions, angiomas, angiokeratomas, pyogenic granulomas, and hemorrhage vasc. Now click on try again. Click on choose file. Select the image, click on open, click on upload button. This is the uploaded image and it is predicted as melanoma is a kind of skin cancer that starts in the melanocytes. Now click on try again. Click on choose file. Select the image, click on open. Now click on upload button. This is the uploaded image and it is predicted as A dermatofibroma is a common overgrowth of the fibrous tissue situated in the dermis, the deeper of the two main layers of the skin. In this way, by uploading the image, we can predict the type of skin cancer. Now click on sign out button here. The conclusion of the project is the project successfully developed robust deep learning models specifically designed for accurately classifying different types of skin cancer. Addressing the class imbalance issue signifies the model's ability to make precise predictions despite variations in data distribution. Achieving high classification accuracy and loss accuracy using an optimized convolutional neural network CNN demonstrates the effectiveness of the model in classifying skin lesions. By leveraging deep learning algorithms, the project significantly enhanced the speed and accuracy of skin cancer diagnosis. This improvement potentially leads to earlier detection and subsequent treatment, crucial in combating the progression of the disease and improving patient outcomes. Implementing an end-to-end smart healthcare system through an Android application signifies a practical tool for assisting doctors in making informed diagnosis of skin cancer at early stages. This system serves as a user-friendly interface, potentially empowering healthcare providers with efficient and accessible diagnostic capabilities. The project's contributions extend to the broader field of AI assisted diagnosis and skin cancer classification. By striving to enhance accuracy and efficiency in clinical evaluations, this work paves the way for more reliable and effective diagnostic support systems, potentially revolutionizing the way skin cancer is diagnosed and treated.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.